Hello, everyone.
Let me put your slides up here, and then I'm gone. The stage is yours.
All right. So today I'm going to talk to you about how we're using Bevy at Metabuild to create a building design application that runs in the browser. So just a quick word about me. I'm Alix. I've been working at Metabuild for about 3.5 years. And during that time, I've used Bevy to create or to contribute to the app I mentioned, and also Rust for various other parts of our infrastructure, such as, for example, setting up lighting simulations and other things. So what we're doing at Metabuild is we are creating a platform, an online platform for real estate developers so that they can create digital twins of their buildings. And the platform will automatically determine the best possible renovation timelines for their buildings so that they can fulfill the various regulations regarding CO2 emissions, energy consumptions, thermal and lighting comfort of the occupants, etc. So the way our platform works is that basically you start by creating a baseline model of your building with our app. There are basically two scenarios where our app is useful. Is basically either you have an existing building that you want to renovate, or you have a new building project, in which case you just want to see improvements upon your current design. So you start by creating the baseline, and then we can then simulate a bunch of properties of that building regarding daylight, thermal properties, electricity consumption, energy consumption, etc., and generate a bunch of scores based on building standards in order to evaluate the building. And then we have a process that basically is an optimization where we generate 1,000 variants of that baseline. So in the case of renovations, these variants will basically be specific renovations in specific years in the future. And in the case of a new building, there will just be improvements upon your design. And at the end, you can get, of course, generate a bunch of analysis reports, performance certificates for the buildings that pass them, etc. And this whole thing is a fully configurable process, so you can adapt it to local regulations as well. So where we're using Bevy, finally, is our modeling applications, as I said, which is a core part of our platform. It runs on the web, and we can use it to draw and configure building models as well as visualize the analysis results. So I'm going to do a quick demo of what it looks like. That's what it looked like. Basically, you can see we have a little map render that uses data from OpenStreetMaps. You can either start drawing a building manually in 2 dimensions, or you can just use one of the existing buildings here from the map. We have a little wizard where you can configure a bunch of things, specify where you want to see which walls should have windows, that kind of thing. This is mostly just a helper, as you can also do everything manually. And then you can, basically it's a design application, right? You can change a bunch of properties. You can change stuff in 3 dimensions or in 2 dimensions. The building is composed of a list of stories, right? And every story has its own floor plan with the walls. The walls are represented as a graph. And you can, of course, draw a bunch of things. And there's also a pretty extensive sidebar here where you can use it to navigate between objects. So this is all powered by custom relations. not really using the default Bevy relations, unfortunately, because we started this before they even were in Bevy. But yeah. Then of course you can run the optimization process that I mentioned in order to find rate a bunch of different variations. And you can also use the app to visualize some of the analysis results. So this is, for example, an analysis result of daylight simulations. This shows the illuminance that the different spaces are receiving throughout the day, averaged over a whole year. Yeah. So basically, our data model is composed of two things. There are objects and settings. Objects are just buildings, stories, windows, walls, that kind of thing. And settings are properties that are assigned to these objects. So construction materials for the walls, shading systems for the windows, usage schedules for the spaces, etc. As you saw, the stories are composed of a graph. It's actually a half-edge graph, to be specific. There's one for the walls and one for the roof, which also has height information in order to create all kinds of crazy roof shapes. And this, the graphs are both entirely contained in the ECS. So vertices, half-edges, edges, and faces are just entities, basically. Our model is defined in a dedicated crate with its own Bevy plugin. We call it the Beam plugin. And it defines objects and settings using entities. It's fully headless, so there's no visuals and no interactivity, because then that makes unit testing easier. We can test a bunch of things without having to worry about those things possibly breaking, and it just separates concerns better. For saving and loading the model, we're just using the standard Bevy's dynamic scenes to serialize the model to JSON. And then we have a separate dedicated type registry, which only contains the model components and resources. Yeah. Of course, when we evolve the model, we have to add fields to components on this kind of stuff. So we have a migration process, which is really simple. We just basically store a version number next to the scene. And then we have a bunch of functions that are whose role is to just migrate from one version to another. One kind of one pitfall to avoid is in the functions that migrate the model, you shouldn't deserialize the JSON values to types, because if you do that, then you're going to have to keep those types around forever, and we obviously don't want that. Another interesting aspect that the Beam plugin defines is there's this issue of having some redundant calculations, right? For example, here, if I want to know the elevation of the floor of story 2, I'm going to have to basically just sum up the story heights of the stories below. Simple calculations, but it does require me to query more entities. One solution to that could be to use a system param. But if I do that, then it's going to be recomputed every time, and it also borrows more entities and more components. And there's a better solution, which is to basically just add extra components and entities on top of the model. These, we call them the cached state. And we don't store them in the scene, obviously, because we can always just recompute them. And a nice bonus of this is that it makes change detection easier. For example, here I can just use the changed query param with the floor elevation component that we add on stories, and just do change detection with that directly. A quick note about how we actually implement the interaction and rendering. We have we need both 2D and 3D representations of the same BIM objects. And for this, I recommend just actually having separate entities. If you need this, you can have separate entities for both representations, with one plugin responsible for each, and that makes things easier because you can't really have 2D and 3D representations on the same entity with Bevy. For UI, we're using Bevy GUI for now, even though of course we're really excited to see how Bevy UI evolves, especially in the coming releases. And the way we're doing it is basically all the top level containers like the sidebar and header and footer. They are basically just an exclusive system that creates the container, and then inside the container we call a Bevy schedule. So for the different, if you want to add some new content to the sidebar, all you have to do is just to add a new system, a new system to the sidebar schedule. And of course, you have to make sure that you order it properly with the other systems. But yeah, it's a pretty simple way to do it and really convenient. We just insert the UI struct from eGUI into the world when we do that. Now I'm just moving on to some random things that we learned along the way while building this. One thing is, especially with application like this, which is pretty geometry heavy, it's super important to have good debug tooling. So it's a good rule of thumb to just add a bunch of buttons somewhere, hidden somewhere, that you can click that will visualize things about your scene. Especially while we're still waiting for the editor to pop up. But yeah, other valuable tools is Bevy eGUI inspector, which you can use to inspect your scene. I mean, it's pretty well known nowadays in the Bevy community, but you can see all of your entities and resources and assets and inspect them, modify them. That's really useful. And another one is Bevy mod debug dump, which shows you graphically displays a graph of your schedules, which is really useful when you have system ordering ambiguities and you want to track them down. One constraint that we have is we want to be able to run our app on a laptop that is on battery. So there is a when it's setting resource in Bevy that lets you change the update mode to reactive. Reactive mode basically just avoids updating the app if there are no input events. So that's something that we want. But we also have animations, as you may have seen when you remove the camera. The camera takes a bit of time to actually come to a complete stop. And so we have to switch, we have to be in continuous mode most of the time, but when no interaction happens anymore, we wait a few frames and switch to reactive mode. But there's a bit of a pitfall with that, is that when you switch back to continuous, you have to be aware that the delta times that you read in the update schedule kind of lag a couple frames behind sometimes. So when you switch back to continuous, you may see like a sudden jump, and that's just the delta time from a few frames ago where you were still in reactive mode. So it's what we found to be a good solution for this is to set a max delta time for a few frames when switching back to continuous mode. Lastly, some words about running on the web. Unfortunately, WebGPU is still not fully supported on all browsers and platforms. And unfortunately, we also saw some bugs with WebGL2 implementations on some platforms and some browsers. Our solution ended up just being compiling the app twice, one with WebGL2 and one with WebGPU, and we just use a bit of JavaScript code to select between the two based on what is supported. Another kind of headache with the web is multi-threading. So you have to use web workers, which are basically just a binary a separate binary WASM that runs in a separate thread. And for this, you can use the glue worker crate. It has a nice little API that looks like calling a function, but it's actually serializing the arguments and passing them to the web worker. But unfortunately, because it's serializing arguments, it's a bit there's an overhead, so it's a bit slow. And another crate that you can use is WASM thread, which has an API similar to the STD thread, so more convenient, but unfortunately it requires nightly and some extra compiler flags. So yeah, still experimental. And last thing is the WASM32 target has a maximum memory usage of 4 gigabytes. So in that case, the solution is just don't use more. But yeah, it's good to be aware of it. And there is an alternative target, WASM64, in the Rust compiler, but it's still in support tier 3, so it's not a first-class support, so it's still experimental. Last closing notes is if you find this interesting, we're hiring, so feel free to get in touch. I'll be happy to answer any questions.
Hey, Alex, super. Thank you so much. That's super exciting to see Bevy in production on the web. So as you can imagine, there's a lot of questions regarding that specific aspect of it. So let's dive into it. Do you have some pro tips to reduce the WASM size? How big is the client at Metabuild?
Oh, it's actually pretty big. It's pretty big, but we're doing some caching, so you only don't download it once. But yeah, there are some ways you can reduce it. There is WASM opt, which is a tool that just takes your WASM as an input and applies some optimizations to it to reduce the size. And obviously, there's also I think a flag that in the cargo tunnel there are some some flags that you can set. Forgot exactly. Yeah.
But what size are we talking about in your case?
Good question.
Roughly?
I can I can look at it and tell you directly. All right, let's.
Well, that.
That work. Okay. Yeah, pretty big. 182 megabytes. That's
wow.
a lot, obviously. But
and that is just one of the two rendering types.
Yeah. So
oh wow.
Yeah, but we only don't download one of them, of course.
Yeah.
But,
yeah. Okay. So the JavaScript magic decides which one's appropriate.
Yeah, exactly.
Okay.
Yeah. But the caching is super important because otherwise the loading times would be absolutely horrible.
Yeah. All right. The next question is, how does this differ from Autodesk Forma, and what does it do better? I have no idea what that is.
I don't really have experience with it, to be honest.
Okay.
But I know that one of our guiding principles in terms of UX design was mainly to actually reduce the just make things easier as possible and incremental. So I don't know how it compares to that specific app, but what we try to do is to make it so that you can start with a really, really basic model to get started somewhere, as you saw with the little wizard tool. And then you can just incrementally add more and more specific detail to your building. We try to hide as much of the complexity as possible. So yeah.
So it's about ease of use, user experience, simplicity.
Yeah, exactly. Yeah.
All
we
right.
try to make it as efficient as possible.
And I mean, I'm not sure because I don't know this thing, but I'm assuming Autodesk Forma is not running in the browser. But yeah.
Yeah. I'm not sure.
The next question is, why switch to continuous rendering and then back instead of sending request redraw events during animations? Well, that sounds like a question Francois would ask.
That could probably be done as well. I mean, I guess we started from continuous mode rendering and later realized, of course, we don't want to always update, so we had this little switch. I'm not sure. I haven't really tried sending manually those redraw events, but maybe that could work as well. Yeah.
There's actually another question that's pretty closely related. How do you detect the animations that animations are running to then be in continuous mode?
We're cheating. We just wait for a constant time after you stop pressing. I mean, we have a we basically have a system that queries a bunch of possible sources of animation, like the camera, and if the camera transform has changed, we have a little timer that will be set back to 0. And after a while, if nothing happened, we switch back. Yeah.
All right, got it. So that's the only type of animation that you're currently considering there, the camera movement.
We have a few more. Don't remember exactly.
Okay, but it's similar. Yeah.
Yeah, it's still one system that is querying for all these possible sources of movement.
Okay, got it. The next one is about backends. Is this thing talking to a backend? What is the API or data model like? And are you using any crates for this?
The backend is just a Postgres database. Our models are made to be kind of self-contained. So, for example, we have the daylight simulations that we have are just another Rust binary that we can run, and it just takes as input the JSON scene of the model. So it mostly just backend is not doing a ton of stuff except moving stuff around. We do actually have a bunch of scripts that are configurable, so you can add extra scripts to derive some information from the model and customize simulations and results.
So when you say the backend is just Postgres, are we talking about a REST API that wraps Postgres, or are you talking to Postgres directly?
Yeah, we're using Postgres actually.
Right. Yeah. So that's like a RESTification of a Postgres database, right?
Yeah, exactly.
Okay. Yeah. Okay. Interesting. All right. So next one, is the WASM app all self-contained with local storage in the browser, or does it need to reach out to any external dependencies or infrastructure? I guess the question is, do you use WebSys to talk to these browser-specific APIs?
I think we have a few of those. We're communicating. I mean, we do use WebSys to communicate to the local storage and store some information in there about just the state of the application. Yeah. Not sure if that answers the question.
I guess. Yeah. I mean, is there any other API that comes to mind that you're accessing other than local storage?
Not really. Or at least none that comes to mind. Yeah.
All right.
Actually. Oh yeah, of course. Yeah, the URL is one of them.
Oh, you mean you read the URL the user accessed?
Yeah.
Okay. So that's the workspace ID that I see there, for example.
Yeah, exactly. Yeah.
All right. That's straightforward, I guess. How do you exclude your cached components from serializing? I think you mentioned that these are not put into the
Yeah.
serialized scene, right?
Yeah, exactly. You can in the dynamic scene there structs there in the using the dynamic scene builder type, you can add component filters and resource filters, and they are basically, as I understand, yeah, they're just lists of like type IDs, I guess. And you
Okay.
can,
So that's how you filter them out. You just provide a list of the ones. Do you provide a white list of what you want or a black list of what you don't want?
a waitlist, because otherwise we would, if
Too
anytime
much.
we add yeah, dependencies, we would have to exclude all of those.
Yeah, makes sense. All right.